We're going to begin by talking about encapsulation. The Open Systems Interconnection Reference Model, or the OSI model, uses a layered approach to enable disparate devices to be able to communicate effectively. During the communication between two devices or nodes, each layer is only responsible for being understood by the corresponding layer on the other device. As data flows down from the application layer through to the physical layer, it is encapsulated at each layer with information to help the corresponding layer at the other end of the communication line understand what is happening. As the data is received at the other end, it is de-encapsulated or unwrapped as it moves up the OSI stack by the corresponding layer. Let's talk about how encapsulation works. The application layer begins the process by sending data that is encapsulated or wrapped with application layer control information to the presentation layer. The encapsulated data is called a PDU, or Protocol Data Unit. The application layer PDUs are segmented by the presentation layer, with each segment being encapsulated by presentation layer control information. They are now presentation layer PDUs. The process of segmenting and encapsulating continues down through the OSI stack until it is transmitted as bits by the physical layer. The receiving physical layer passes the bits to the receiving data link layer, which reads the data link layer PDU information and then de-encapsulates and desegments it, sending the new packets to the network layer as network layer PDUs. The process of de-encapsulating and desegmenting continues up the OSI stack until it is received by the application layer, where it is finally fully de-encapsulated and fully reassembled. This encapsulation and de-encapsulation allows differing systems to be able to communicate together effectively. With that covered, let's move on to modulation. The physical layer of the OSI stack is responsible for transmitting bits of data across some form of media, so it literally is responsible for transmitting zeros and ones across the media like a cable. The question arises, how does the physical layer transmit the data across the media? The bits of data are modulated or encoded by the physical layer and placed on the carrier signal of the media, which carries the modulated data onto its next destination. The carrier signal can also be referred to as the carrier channel. Once the bits are received, they are demodulated or unencoded by the receiving physical layer. A carrier signal is a standard waveform, usually in the form of a sine wave, that is used as the base carrier of another input signal. A sine wave is a mathematical curve that is represented by a smooth repeating oscillation. Now let's define modulation. Modulation is the process of varying one or more properties of a carrier signal with an input signal, usually for the purposes of conveying information. Modulation can be used to encode digital network traffic onto media that uses a digital carrier signal, as in using an ISDN connection between two networks. Modulation can also be used to encode a digital signal onto a media that uses an analog carrier signal, as in digital network traffic traveling over the public switched telephone network, or PSTN. Multiplexing is often used with modulation. Multiplexing can be used to increase the number of modulated signals that can be placed onto a carrier signal. So let's talk about multiplexing, and I don't mean your local movie theater. The type of carrier signal will determine if multiplexing can occur. A baseband carrier signal cannot have multiplexing occur, as the modulated signal will consume all of the available frequency or channel width. Multiplexing can be utilized on a broadband carrier channel, as each modulated input is assigned a portion of the channel width of the carrier channel. Multiplexing can use one of two methods to weave streams of modulated signal into the carrier signal. There's frequency division multiplexing. This is the process of mathematically dividing the carrier channel frequency into multiple segments and assigning the results to modulated input signals. Then there is time division multiplexing. This is the process of mathematically dividing the carrier channel width into multiple time segments and assigning the time slots to different modulated signal input streams. It's time to talk about the difference between a baseband and broadband carrier channel. And we're going to begin with baseband. A simple definition of baseband is a stream of data that is sent over a carrier channel as a digital modulated signal. The digital signal will take all of the carrier signal's available frequency or time. While the modulated input does take all of the carrier channel's available frequency, the communication is bidirectional. It can flow back and forth. A simple definition of a broadband carrier channel is a stream of data that is sent over a carrier channel as an analog modulated signal. The analog signal will be assigned a portion of either the carrier channel's available frequency or time. While the modulated input doesn't take all of the carrier channel's available frequency, the communication is not bidirectional. For two-way communication to take place, multiplex channels must be created. That is, a channel for each direction. I'm going to begin with network transmission concepts. The first concept is wavelength. Wavelength is a measurement of the distance between peaks in a wave pattern emitted by electromagnetic radiation, as in light waves, radio waves, or microwaves. Each type of electromagnetic radiation falls into a specific range of wavelengths. By modifying a wavelength, data can be encoded into the wavelength and transmitted to a receiving device, which then decodes the transmission. Then there's baud rate and bit rate. The baud rate was originally used to measure the speed of a telegraph transmission. It is a measure of the number of state changes in a given period of time. The usual state change that was measured was electricity, as in the number of times the state changed from 0.5 volts to 1.5 volts. The bit rate is a measure of the number of zeros and ones that can be transmitted across a medium in a given period of time. So it is a measure of the actual bits that can be transmitted. It is usually measured in bits per second, or BPS. The bit rate is a more accurate measure of transmission throughput than the baud rate. Then there's sampling size. When converting from an analog audio signal to a digital signal, a computer or other device captures the analog audio waveform and mathematically converts the captured sample into different wavelengths, which is how we get the discrete sounds. This occurs over a specific period of time, which is called the size of the sample, or the sampling size. And finally, there's carrier detect and carrier sense. Carrier detect is when a device can only tell when a carrier signal or channel is present by the reception of a control signal. The presence of the control signal signifies that transmissions can occur. The control signal controls the order of transmissions, so data collisions are not possible. The control signal can also be used to establish the maximum speed of the transmission that can be used. Carrier sense is when a device uses feedback from a receiver to determine if a carrier channel is present. If a carrier signal is detected, the device can send transmissions. Data transmission collisions are possible with carrier sense. And that logically leads us into CSMA-CD and CSMA-CA. The carrier detect method of network transmission works well when there are just a few nodes that need to be connected together. However, as the number of nodes that need to transmit increase, the efficiency of carrier detect begins to decrease to the point where it can become unmanageable. Although the carrier sense method of network transmission is not as efficient when the scale of the network is small, as the number of nodes increases, it becomes more efficient than the carrier detect method. So let's talk about CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. CSMA-CD, of course, uses the carrier sense method of network transmission. Every device on the network uses feedback from a receiver to determine if a carrier channel is present. Every device connected to the network has an equal opportunity to place a transmission on the carrier channel. That's the multiple access part of the name. Before placing a transmission on the carrier channel, a device will listen to the channel to determine if another node is transmitting. If it detects a signal on the carrier channel, the node will wait before attempting to transmit. If no signal is detected, the node is free to send. If two devices send a transmission at the same time, a collision between the transmissions is possible. Sending devices will listen for transmission collisions. If a collision is detected, a jamming signal is sent informing all nodes that a collision has taken place. All devices that receive the jamming signal will wait for a random amount of time before attempting to transmit. Now let's talk about CSMA-CA, or Carrier Sense Multiple Access with Collision Avoidance. CSMA-CA operates in the same manner as CSMA-CD with one exception. It uses a collision avoidance scheme through the use of a controlling device. Before attempting to send data, a device will place a specific signal on the network called a request to send packet, or RTS packet. If no other device is utilizing the network, the controlling device will respond with another specific signal called a clear to send packet, or CTS packet. Once the sending device receives the CTS, it knows it can send a transmission without a collision occurring. CSMA-CD is better suited for high-speed, high-throughput networks and is the specified network transmission standard for the 802.3 Ethernet networking standard, as it has a low amount of network overhead. CSMA-CA is better suited for lower speed, lower throughput types of networks where the possibility of data collision is higher. It is the specified standard for 802.3 wireless networks, or Wi-Fi networks. I'm going to begin by talking about numbering systems. While computer code and communication can get very complex, it can also be broken down to a basic bit level. A bit has one of two values. It either has a value of 0 or it has a value of 1. These values can be thought of as being either off, which is a 0, or on, a 1. These bit values are actually the only information that computing devices know. By combining and adding different bits together, computers can communicate with each other and programs can be created. Because of this, technicians need to know how to work with binary, or the base 2 numbering system. Binary is a base 2 numbering system where each position has one of two basic values. It is either a 0 or a 1. It is written from right to left with the potential value of digits being doubled with each additional digit that's added. If a 0 is the placeholder, it has a null value or no absolute value. And if a 1 is present, the actual value is double the potential value of the digit to the right. To derive the final value of a binary number, add all of the potential values together, and that will give you the decimal value of the binary number. The binary numbering system is very important when dealing with computers and networking. You should become comfortable with converting from decimal, or base 10 values, to binary, and from binary back to the decimal format. If you need help with that, there are multiple websites that can help. One website that I recommend is mathisfun.com. You can look on their website for their binary numbering lessons. Now let's talk about bit, byte, and nibble. A bit is a single 0 or 1. A byte is 8 bits, and it can also be referred to as an octet. A nibble is half of a byte, or 4 bits. and these terms are used quite frequently when dealing with binary. Now let's talk about hexadecimal. Hexadecimal is a base 16 numbering system that uses the numbers 0 through 9, and then it uses the letters A through F to represent the values 10 through 15. It functions in the same manner as binary, but with base 16. Each hexadecimal digit has a potential binary value of 1111 or 15, and it can be referred to as a nibble as it's half of a byte. A hexadecimal number can often be recognized by the notation prefix of 0 lowercase x, which directly precedes the hexadecimal number. Hexadecimal is widely used in programming and networking along with binary. Some examples of binary and hexadecimal use include IPv4 addresses, which can be represented by a 32-bit binary number that is divided into 4 8-bit sets. Each 8-bit set is equal to 1 byte and is often called an octet. An IPv6 address, which is a 128-bit binary number, is usually represented by hexadecimal, and it is divided into 8 2-byte sets, each set being separated by colons. And I recommend that you watch my presentations on IPv4 and IPv6 to get a better understanding of how binary and hexadecimal are used in networking. And now let's move on to conversion tables. When working with binary and hexadecimal numbers, I recommend creating a conversion table before doing the math. I find it to be very useful when I need to convert from decimal to binary or from hexadecimal to binary to decimal.